This handout looks at the reactions of carbonyls where the carbonyl carbon bears a leaving group. And so these are functional groups that are the subject of chapter 20, so carboxylic acids and their derivatives. And again, I've provided the relative reactivity of the carboxylic acids and derivatives together with the aldehydes and ketones shown in the middle. And this order was discussed in the table, the video that I did of the table previous to this. So in terms of the relative reactivity, there are two factors that mercifully don't fight each other. So first of all, in the original carbonyl, you have the effect of resonance. So Z is the group that could be the leaving group. So it's going to be an OH for carboxylic acid, OR for an ester, Cl for an acyl halide, say NH2 for an amide. So all of those atoms that I said have a lone pair on the atom that's directly attached to the carbonyl carbon. And so there is the potential for this second resonance contributor. This resonance contributor is not nearly as electrophilic. This carbon is not as electrophilic as this carbon. So if you have a functional group where this resonance contributor is more significant, then it's not going to be as reactive. And it turns out that this resonance contributor is pretty significant for amides. There's a decent amount of double bond character in the carbon-nitrogen bond of amides. And it's least significant for acyl halides, which are more electronegative and, say in the case of the chlorine, differently sized than the carbon atoms. So again, the second resonance contributor inhibits the carbonyl electrophilicity and makes it less reactive to nucleophiles. You can also look at this from the standpoint of inductive effects. So if you have an electron withdrawing group on the carbonyl, it makes the carbonyl more electrophilic. And I've pulled out chlorine versus oxygen versus nitrogen, so acyl halides, carboxylic acids and esters, amides. Chlorine is electron withdrawing by induction, and although it has the potential to do this resonance effect, it's not very good at it. So it's way, way better at being an electron withdrawing group than an electron donating group. Nitrogen is the exact opposite. It's not particularly good at being an electron withdrawing group by induction, but as we saw, it's a good electron donating group by resonance. So that makes the amides the least reactive. And then the two groups with oxygen, the esters and the carboxylic acids, are in between. The oxygen is potentially electron withdrawing by induction, but it turns out it's a little bit better at being an electron donating group by resonance and therefore less reactive than the halides, more reactive than the nitrogen. You can also look at leaving groupability, which works because remember that no matter what the circumstance, a good leaving group, or I guess I should say a better leaving group, is a weaker base. So if you look at the leaving groups in this series of compounds, chloride is the leaving group from acyl chlorides. That's neutral, therefore the best of the leaving groups. Anhydrides, you have a weakly basic leaving group. Esters and carboxylic acids, a strongly basic leaving group. And then with the amides, you have a very strongly basic leaving group. So that's the worst leaving group, the best leaving group, adequate leaving group. Something that in the past we've actually said is not a leaving group, say in Chem 21, although we saw in the alcohol chapter that, yeah, well, sometimes it does leave. So if we write out an overall simplified reaction for what happens with carboxylic acids and derivatives, you start with your carboxylic acid or derivative, the nucleophile attacks, and just as we saw with aldehydes and ketones, you get this tetrahedral intermediate. What's different here is that since there is something that can act as a leaving group, this group Z, you can reform the carbon-oxygen double bond, which is a strong bond and part of the driving force for that, and end up with a nucleophile now attached to the carbonyl carbon and the group Z left because it's the leaving group. And this particular reaction is known as a nucleophilic acyl substitution. Note that it is 2 steps. It's not an SN2 reaction. It is not a direct displacement. Please do not do that on a test or a quiz. So if we look at this first step, and I've written these as equilibria. So if we look at this first step, the forward reaction here is helped if Z is an electron withdrawing group and if the nucleophile is good. So I guess I should say and the nucleophile is good. I'm not trying to imply about Z being a good nucleophile. And in this second step, the forward reaction is helped if Z is a better leaving group than the nucleophile is as a leaving group. So in other words, you have this tetrahedral intermediate. You compare the leaving group abilities of Z versus the nucleophile. If Z is the better leaving group of the two, it goes the way we want it to go. If the nucleophile is the better leaving group, it goes back that way. If you have a scenario where Z and the nucleophile are equally good at being leaving groups, equally basic roughly, then you have a scenario where it kind of goes, as the scarecrow points in The Wizard of Oz, in both directions. So for these reactions, the overall reaction is going to be greater than K. It's going to proceed towards products if Z, the thing that played the role of the leaving group, is a weaker base, a better leaving group than the nucleophile. K is going to be less than 1, and you're going to not tend to see those reactions if Z is a stronger base than the nucleophile. And this is just acid-base chemistry. Remember, these acid-base reactions proceed towards weaker acids and bases. And so if Z is the weaker base of the two, it goes this way. If the nucleophile is the weaker base, it tends to be shifted this way. And again, K is going to be about equal to 1 if the nucleophile and the leaving group have similar basicities. And both David Klein and Professor King explain the kinetic equilibrium aspects of this with reaction coordinate diagrams. They both do a good job. I'm not going to revisit that. So a little bit more on the mechanism. So all of these nucleophilic acyl substitution reactions have the core steps where the nucleophile attacks and the leaving group leaves. That's what we saw in this reaction. They may have additional proton transfer steps depending on the pH at which you're doing the reaction, or more fundamentally, how reactive the carbonyl and the nucleophile are. If you have a more reactive carbonyl, it's not going to need help. It's not going to need to be protonated. And if you have a better nucleophile, the reaction is less likely to need help. So you can help these reactions in 2 ways. You can either do the reaction under basic conditions, in which case you're providing a better nucleophile, or you can do a proton transfer to the carbonyl and make that carbonyl more acidic, just like we saw with the reactions of the aldehydes and the ketones. And in fact, I think nucleophilic acyl substitution is easier than the reactions in chapter 19. So again, you may need proton transfer steps in addition to the core steps of the nucleophilic attack and the departure of the leaving group. So I've written out the worst case scenario here. The maximum number of possible steps is that in addition to the nucleophilic attack and the departure of the leaving group, you have 1, 2, 3 proton transfers. So again, I'll do this, I'll do that. You're going to need this first proton transfer step if the carbonyl needs help to react. If you're looking, let's say, at an ester or a carboxylic acid, that's one option that you can do. And then related to that, if you had to do a proton transfer in the first step, then you're going to have to remove it at the end. And another case is if you make, say, a carboxylic acid and base and you need a separate acidification. But generally speaking, if you need to attach a proton here, you end up removing it. And then in the middle, you have proton transfer steps. So if your nucleophile is charge neutral, like it's an alcohol or water, you'll need a proton transfer step. And also, if the nucleophile, or the nucleophile needs a proton transfer to make it into a better leaving group. And what I really meant there was the leaving group needs a proton transfer to make it into a better leaving group. We're not making the nucleophile into a leaving group. So you'll end up with these proton transfer steps. Again, anytime you have a charge neutral nucleophile, you're going to have to remove a hydrogen from the heteroatom. And then if your leaving group needs a proton transfer to make it into a better leaving group, then you'll have proton transfer. And notice that this is an and or. So it's possible that you'll end up with two proton transfers, one off the nucleophile, one onto the leaving group. And remember that in general, protons don't hop. So when you're writing mechanisms and you're doing proton transfers, if you ask yourself the question, do I need to do this in one proton transfer or two? The answer is usually two. So some students find it helpful just kind of to remember the sequence, proton transfer, nucleophilic attack, proton transfer or transfers, departure of the leaving group, possible proton transfer, just kind of as a check to what you're doing. And finally, one more thing, because I didn't know where else to put this. If the product of a nucleophilic acyl substitution is more reactive than the original carbonyl compound, there may be a second nucleophilic addition. We saw this back in the alcohol chapter. So you could take an ester, you could reduce it with an excess of lithium aluminum hydride, and that gives you an aldehyde. Well, we now know that aldehydes are more reactive to nucleophiles than the original ester, and so this reaction will just keep rolling along, and there's really no way to stop it at the aldehyde. It's going to go all the way to the primary alcohol. One thing we'll learn in this chapter there are some tricks that you can use to stop at the aldehyde, the more clever of which base themselves on the fact that they start with a highly reactive acyl halide and make a less reactive aldehyde.